All right, everyone, we are back and we are basically going to start on our lecture 9 where we're going to look at analyzing and starting to get into, we preface this idea about controls about we need a system that's stable, a system that's robust, a system that's responsive. Um, and we've started to see that if we tune the poles of our transfer function of our system, of our plant, or of our controller, whatever. I mean, we're getting a little ahead of ourselves, but we see that we can tune the poles and the zeros of our system in order to change essentially the response of that system. Now, we need to now start to think about how are we going to analyze what are the numerical metrics, what are the specifications that we need to hit for a specific design. So, for example, let's say I wanted to create my own universal testing system. So usually if you've done any, work with an Insteron, you have kind of these two rails that are ball screw driven. You have basically this top head with fixtures and a bottom head. One of those is fixed, one moves. Let's say the top is the one that's moving. You put your sample in between the grips. You put in tension, compression, et cetera, et cetera. So if I'm designing a control system, something like this, I need to know, or I'm going to want certain specifications, right? Like if I need to measure, I need to have the ability, I need my displacement rate, the displacement rate of essentially my grip distance to be something like I need to run at, 60 millimeters per second. Maybe that's my top end, specification that I need to hit. Maybe I need to have a resolution or a step size, I need to be accurate to 0.1 micrometers in terms of my disc. So there are certain specifications that we may have to hit, and we have to kind of tune that to essentially modeling the equations of motion of this system. The controller will essentially turn these ball screws, and then we have to figure out how do we kind of have these real-time specifications. But remember, we're working with a transfer function that's in the S domain, and how do we correlate the two? How do we make sure that we actually design and create experimental apparatuses that will hit what we want to do experimentally? So that's kind of the motivation for we're going to actually look at kind of the time responses of our system, and we're going to actually see, okay, like, are we, or if you can kind of even think of, if I have a spring mass damper system, like a shock absorber in a car. So I have, the wheel, I have my shock absorber, I have the car. There's only a certain amount of distance that if I overshoot and this wheel goes up, if it overshoots my maximum allowable distance by, 30%, I'm going to crash into my chassis. That's not good. So we have to kind of understand and figure out what's going on with these systems. So a lot of systems that we're going to work with, and ones that show very distinct behavior. Second order systems, we've already talked about it with, again, our famous spring mass damper system. Similar idea with a kind of a torsional pendulum as well. And this is how we're going to describe. This is our transfer function for those systems. Now, you see it's written in two distinct ways. Both of these are critical. Both of these are important. We need to be able to work between each of these, definitionally and understanding. So this is just, again, you've kind of probably seen this before. So we can write it essentially here. We have sigma, we have omega. This is probably something that you've seen more in your vibrations class, where you have omega n, the natural frequency of the undamped natural frequency of our system, the damping ratio, which you're all familiar with, where if our damping ratio is greater than 1, we're overdamped, no oscillations. If it's 0, undamped, pure sinusoidal. If we're in between 0 and 1, again, typically probably around like 0.5, 0.4, we're underdamped. And if our damping ratio is equal to 1, we are critically damped, and that's our fastest, essentially, response. So this is our transfer function. We're going to work with this, and we're going to kind of see how we can relate some of these parameters and some of these parameters that we want to hit, right? So there might be particular values, and vice versa, right? We might want certain time domain specifications. We might need to tune some of those parameters in order to hit those, right? So we might need to increase the damping. So increase our C. We may need to increase our stiffness in order to get a more damped response if there's too many, again, you can kind of start to see we're going to make a connection between the response of the system and those physical parameters. That's always the most important kind of aspect here. So let's get to it. And we're going to actually first see how we can kind of visualize this in our S domain again, because we're going to create basically the goal of this is also to create in our S domain a region where, based on one metric, it has to be in this region. Based on another metric, we have to live in this kind of region, and based on another metric, we have to kind of lie, in this cube or this so we basically want to kind of find like the Venn diagram where we can hit each of these different, we can lie in the region that satisfies all the conditions that we want. So that's effectively our goal. So this is our second order transfer function. We do have some values of zeros, but again, the poles determine the response of the system. That's what we're interested in right now. And this is what we're looking for. So we have one pole that is essentially real. We have our imaginary pole here, sigma, omega. And we can start to plot those out. Now, before we go up to that S-plane, we can also look at the system here. And we can solve, and we know that the poles of our system will be equal to this. So here are some definitions. Before we do that, let's look at this geometrically. So if I look at this first part, my imaginary value is omega. So here, this is omega. Same thing here, minus omega. There's some symmetry things that we're going to kind of talk about and show in later lectures. That we know that the real axis intercept is going to be minus, and it's going to basically be here. This is going to be this distance from here to here. That's going to be my sigma. So you can look at it from that perspective. I always think, in this, again, we can't just ignore this this framework and this idea, but I want to now kind of make the connection to this system where I think we're more familiar with, and there's more of a physical connection because we have the damping ratio, we have the natural frequency of our undamped system, which we know, and we can actually relate that to our stiffness and the mass essentially of our system as well. So if we think about it, so this is effectively, this distance here is also omega, and we can start to do essentially some math to kind of play around and to define some of these parameters. So actually, not only some math, some geometry. So we can see here, if we look at, or if we define, based on this, our value here, omega is going to be equal to omega n equals omega n square root 1 minus lambda squared. Or zeta squared, excuse me. I'm always bad at this one. Eta squared. Or zeta squared. Yeah, I'm going to make damping ratio squared. We could also relate that this is going to be equal to, let's go down here, damping ratio minus, or basically equals damping ratio omega n. So that's just kind of relating the same things, and you can kind of rewrite these, but there's some really important parameters there's a really, really important parameters here that we need to kind of relate, and essentially how we can kind of describe essentially some angles, and basically the idea that we're going to live, basically the poles are going to lie, essentially this idea, in a radius, or a semicircle with a radius of omega n centered at the origin. And then we're going to have this right triangle here where we can kind of define it as such. So let's go ahead and let's see how that comes to play. So we can actually define, if we don't know, or if we didn't know what this is, I can go ahead and actually, let's set this up. So we can define essentially this right triangle. So if I want to find out what that hypotenuse is, I can write it in terms of omega and sigma, but that's not really helpful. But when we know omega n, I'm going to say, I'm going to call this side 1, side 2. So my side 1 distance is omega n times square root of 1 minus zeta. I'm going to call it zeta squared. S2 equals zeta times omega n. So we know that our hypotenuse must be square root of S1 squared plus S2 squared. And we're going to say solve a squared plus, actually, let's just do S1 squared plus S2 squared equal to X squared. And omega n, just to prove it. Again, I know this is a silly exercise, but I think it's a good, idea. So that's how we're going to relate this. The magnitude of this hypotenuse is just that. It is that omega n. So we can derive and we can show that. Now, what about this angle here? This angle is going to be our theta. And here we're saying already it's equal to basically sine of our damping ratio, our damping coefficient. So we know that theta equals opposite. So what is this distance here? That's our S2, correct? Yes, indeed. Over hypotenuse, which is omega n. Actually, sine of theta is that. Opposite of our hypotenuse. So what we'll do is we can see, and we'll do S2 divided by omega n. So opposite of our hypotenuse. And indeed, that's zeta, and that gives us the value. Again, I know that this may seem trivial at this point, but again, we need to understand and have an idea of where these relationships come from based on the poles of the system and how we can sketch out the S domain and how we can work between these definitionally. So we have to know this, and it's good to know essentially that connection as well. So that's kind of the idea. And these are kind of definitionally, and we have to make sure that we know these definitions. All right. So that's kind of your first introduction. We'll come back to that. It's our foundation. And then we're going to also now define essentially the standard time domain performance metrics and then connecting them to some of these parameters that we just defined now. One quick note about what we're going to be doing moving forward. A lot of these are empirical definitions. So they're not derived fundamentally. They're approximations a lot numerically. So again, we don't like to do that, or I don't like to do that. It's great to have that fundamental understanding, but we're going to show you how you would calculate it, but we're going to use those definitions, so just be ready to work with them. So thanks. See you next time.